In this video, we're going to look at the dot product of vectors. So we've already done a few operations with vectors. We've done adding. So for instance, when you add these two vectors, you get another one. And we saw that that had some geometric meaning. We also saw that you can scale vectors. So, let's just say like E times AB is just another vector, E times A, E times B. So you'll notice that we haven't done things like, we haven't multiplied vectors together or divided them. And the reason is because you can do that, but it doesn't mean anything in terms of the geometry. So like we saw the graphs of this addition, we saw what that meant in terms of the graph, the tail to head model. And then likewise we saw what this scalar multiplication meant in terms of the graph. Multiplying two vectors together, meaning multiply u1 over, u1 times v1, and then multiply u2 times v2. I mean, you can do it, but it doesn't mean anything. And same with dividing. It just doesn't, it has no meaning, so you'll never see that. But the dot product of two vectors does have actually an important significance regarding the geometry. So, and we're going to see that in a second. But first, we're just going to get comfortable computing the dot product because it's very easy to compute. So we might as well start there. If you look at the definition here of the dot product, given two vectors with these components, then the dot product, notated with this dot, is just the product of the x components added to the product of the y components. And then you get some answer. Okay, so it's really easy to compute, and we're going to do that now using these three examples. So in the first example, you get the dot product. And again, how do you know you're doing the dot product? There should always be a dot right in between. So just look for that. 2 times -4 plus, I add it to the product of the y components, and I get -8 plus 3, or -5. So one thing you notice is that I don't get another vector. I get a number, or what's called a scalar. So the dot product produces a scalar, not another vector. Let's try this next one. So it would be 5 times 2, the product of the x components, added to the product of the y components. And so this equals 10 plus -10, which is 0. And we're going to see in a second that that's actually really a special result for a dot product. And why don't you pause the video and try this one yourself. Alright, welcome back. You should have gotten 5 times 3 plus -1 times 2, or 15 plus -2, or in other words 13. Okay, so there's how you calculate the dot product. Very simple. But what does it mean? Well, that's what we're going to look at. So we're supposed to draw diagrams for each of the above pairs of vectors, the ones from the previous page. I'm just going to set this up here, which are right here, and draw them in standard position. Then we have to notice something about the angles that are formed between them. So 2, 3, I'm going to graph here. So that's right 2 and up 3. Try that the best I can here. And then -4, 1, left 4, and up 1. Okay, it's not the nicest looking vectors there, but it'll do. Okay, let's go over to this one. 5, -2, that's right 5 and down 2. So that would look like that. And then 2, 5 is right 2 and up 5. Okay, so that looks about right. And then finally, 5, negative 1, right 5 and down 1. Looks like that. And 3, 2, right 3 and up 2. Looks like that. Okay, so what do we notice? What do we notice about the angle between each pair of vectors? And let's record the dot product. You probably have it above, but the dot product here was negative 5, right? So let's just write negative 5 here to remind ourselves. Negative 5. The dot product here was 0, and then the dot product here was 13. So you might be asking, like, what am I supposed to notice? Well, first let's notice something kind of obvious, and that is the middle one. The dot product was 0, and if you kind of look closely at these two vectors, there's this weird symmetry to them, right? They both have 5s and 2s, except one of them is negative. And that resulted in the dot product being 0 when you added them together. If you think about it, even though the notation is different, the slopes of these lines, if you view these vectors as lines, are opposite reciprocals of each other, right? Because the slope of the first one here is up 5, right 2, and the slope of the second one is down to right 5. So again, the slope of the first one, I'll just kind of write it up here, is 5 over 2. And the slope of the one down here is down to and right 5, which are opposite reciprocals of each other. And if you remember from Algebra 1, two lines whose slopes are opposite reciprocals are perpendicular. And so what you should notice is that a 0 dot product means that the angles, the angle between the vectors is 90 degrees. Okay, and if the dot product of two vectors is 0, let's look down here at the bottom. If the dot product of two vectors is 0, as happened in the middle, the vectors are, we say perpendicular, but in when we talk about vectors, we have a special name for perpendicular, which is orthogonal. Okay, orthogonal, as far as you're concerned, just means perpendicular. But because, you know, vectors, I mean, for those of you who go on to math in college, vectors we're in 2 dimensions here, but you can go up to like however many dimensions you want. And when the dot product is 0, we would say the vectors are orthogonal, even though there's no picture for dimensions up past 3. So the word orthogonal is just particular to when we're dealing with vectors. The dot product to the right here was 13, which is a positive number. So positive numbers, positive dot product implies that there's an acute angle, right? The angle between them was acute. And surely enough, when the dot product is negative, the angle between them is obtuse. Now, why is that the case? Well, that's something we can look at in the next video, or you might be able to figure out in the next video when we deal more with finding the angle between two vectors precisely. But for now, calculating the dot product, and the big idea is this middle one here, which is when you get a 0 dot product, you know right away that the angle between the two vectors is 90 degrees.